There is a video from YouTube about solubility and solutions that might be worth looking at if you're not 100% familiar with them. Remember what a solution is. It's when a solute is dissolved in a solvent. And generally speaking, when we're talking about equilibrium situations, we're going to put a salt, which is some or other ionically bonded substance, and we're going to dissolve it, generally speaking, into water. And remember, they are both polar, and so they'll dissolve nicely in each other. And if you've got hardly any salt, you've got an undersaturated solution. In other words, my forward rate is greater than my reverse rate. I've got more salt dissolving in water than the other way around. Saturated means that the forward and the reverse reaction are occurring at the same rate. In other words, that's an equilibrium situation. Oversaturated is when it actually starts favoring the reverse reaction and the salt starts precipitating out of the water. Remember, the salt might be anything. It might be copper chloride, it might be sodium chloride, it might be potassium sulfate. There are all sorts of different salts, and salts are just some or other ionically bonded substance or a metal and a non-metal ion bonded together. So what happens is the following. You're going to have some of the solid particles going into solution. Simultaneously, some of the solution particles are becoming solid again. And so the ions become the solid and the solid become the ions at the exact same rate. That is when you've established an equilibrium. And we can write that as some or other solid breaks up into its two constituent ions. This is known as dissociation. When I want to write a Kc value for that, there's a special name for solutions, and that's KSP, K solubility product. But it's just a refined version of a Kc. There's nothing fancy in it. So obviously I ignore the solids, so it's concentration of products. There they are. Aqueous, yes, or gas, and I put them in. Raise them to the power of the coefficient in front of them, which in this case is 1 and 1, and therefore nothing's written, over the concentration of the reactants, and in this case there is no aqueous or gas reactant, so it's just a 1. So if I take something like sodium chloride, what happens if I decide to add some H3O plus ions and some Cl minus ions? I am putting more of the product in, so I will favor the reverse reaction. So adding hydrogen chloride to the above equilibrium causes the equilibrium to shift to the left. In other words, favor the reverse. Sodium chloride is therefore precipitated until a new equilibrium is restored. Disturbance of the equilibrium by increasing the concentration of one of the two ions is known as the common ion effect. You're expected to know about the common ion effect, and I'm going to show you a video which tries to explain it fairly well.
Soluble solid such as silver iodide is placed in water, an equilibrium is established between the ions in the solid and its solution. In this view, the water molecules that solvate the ions are not shown to simplify the illustration. The solubility equilibrium is expressed by the solubility product. The silver and iodide ions are of equal concentration in the solution. When sodium iodide, a soluble salt, is added, the concentration of iodide ion is greatly increased. This means that the product of the silver and iodide concentrations exceeds the solubility product constant. Because the product of the ion concentrations exceeds KSP, additional solid silver iodide forms until the product of the iodide and silver ion concentration again equals KSP. At equilibrium, when the product of the silver and iodide concentrations equals KSP, the silver ion concentration is much smaller than the iodide concentration.
I can work out the equilibrium constant or determine the equilibrium constant of any salt when I put it into water, and it's an ionically bonded substance, so it's going to dissociate into its two ions, and once it has dissociated, we are going to simply say Kc or KSP, which is called the solubility product, is going to be the concentration of the products raised to the appropriate power over the concentration of the reactants. But the reactants are solid, and therefore I don't put them into the Kc or the KSP. You're going to need to know the solubility of certain salts. Not all salts are very soluble in water. All nitrates are soluble, and all alkali metals, in other words, if it's sodium anything, potassium anything, lithium anything, and they will dissolve really well. Something like ammonium sulfate will dissolve well. Any ammonium salt dissolves well. Most chlorides, bromides, and iodides also dissolve well, except for silver, mercury, copper, and lead. Somehow they seem to have an expectation that you know the solubility of these salts. The rest of the rules over here, I wouldn't worry too much about. They're often a duplication of these three. So try and commission those three to memory. It's useful when we are doing electrochemistry as well, and you're going to need to know it then. But you are expected to have a vague understanding of solubility. What you'll find is that solubility often links to temperature. Most salts, as you raise the temperature, will dissolve more. So potassium nitrate does it beautifully. As the temperature goes up, woo, up goes the solubility as well, and you get more and more grams dissolving in the same amount of water. Same is true of lead nitrate. Interestingly, sodium chloride hardly increases at all. It does increase, but very, very little, and potassium chloride also doesn't increase a lot. If I'm not mistaken, there are a couple of salts that actually decrease with temperature, but I'm not exactly familiar with them. But most salts, as you increase the temperature, so the solubility is going to increase. Looking at acid and base equilibrium, acids and bases, we're going to study acids and bases in a couple of weeks' time, and you're going to sit here now and think, well, I don't really understand acids and bases. But if I didn't teach you equilibrium first, you wouldn't really understand it when I do it then. So it's kind of a little bit of a chicken and an egg. I'm going to tell you a little bit about it. If we say that an acid is strong, it will conduct electricity very well. And the reason for that is because it ionizes in water really well. In other words, the forward reaction is favored. Why do I say ionize and not dissociate? Because the water molecule actually becomes embedded in the ions. I create new ions. I get the H3O plus ion when I'm dealing with acids. You should recognize this acid as ethanoic acid from organic chemistry. It is a weak acid, and when it ionizes in water, forming the H3O plus or hydronium ion and the ethanoate ion, I am going to find that the reverse reaction is favored. When the reverse reaction is favored, we say that that is a weak acid, and it generally conducts electricity very poorly. So that's just something to keep in mind when we start doing acid-base equilibrium in a short while.